Welcome to your lecture on thermochemistry. Today we are going to be looking at definitions and terminology. My recommendation is that you have a pen or pencil and some paper so that you can write down those definitions that you need clarification on, critical information about the definition or that particular term as we go through it. Hopefully by the end of this lecture those questions will be answered and explained for you. But if not, please make sure that you get with your instructor before the assessment so that you can get that clarified or get a better understanding. So let's go ahead and get ourselves started. When we look at definitions, the first thing we need to define is the word thermochemistry in and of itself. Thermochemistry is when energy changes occur during a chemical reaction and a change in state. You all should know that a chemical reaction starts out with reactants and those reactants go to products. Well, the state of those reactions can be different. We could have reactants that are gases, but the product of those reactants are an aqueous solution. For instance, I could have, let me see, two gases. I could have nitrogen, which is a gas, plus hydrogen, which is a gas. And they could create NH3, which is ammonia. Make that 3 a little bit better for you. There we go. Which is aqueous. Now you already know, aqueous. You already know what your states are, and you should have learned that earlier in the year. So we have here two gases that become an aqueous solution. So in addition to the energy that changes during a chemical reaction, we also have energy that occurs, change that occurs as it goes from one state to another. If I'm going from a gas to an aqueous solution, I'm going through molecules that have a high movement to molecules that have less movement. So there is going to be a loss of energy for that to happen. And that E with a line over it means energy. So then thermochemistry, again, is energy changes that occur during a chemical reaction and changes in state. So make sure that you know this definition. Again, pause the video as you go through the video, wherever it is you see fit, so that you can write clarifying information down, write down questions if you have them, or write down critical bits of information. That yellow highlighter shows you a critical piece of information. Chemical potential energy is the energy that is stored in chemical bonds. So once again, we look at reactants to products. Potential energy is reactants here, especially if you're going from a gaseous to an aqueous solution. Your potential energy is the amount of energy that's stored here. When that energy is broken because there is a loss of energy, then your products will have less energy than your reactants because you don't need that much energy to produce your products. The potential energy in your reactants gets released in the equation and making the products. So make sure that you understand the definition of chemical potential energy also. Heat is energy that transfers from one object to another because of different temperatures. A good example of that is when you stand before a fireplace. Notice that you get warm because the heat is transferring from the fireplace into your person. If you walk away from the fireplace and go outside, let's just say if it was snowing probably, then the heat is going to transfer from you into the atmosphere because heat always goes from a higher temperature to a lower temperature, down the temperature gradient. When you have two objects that are different temperatures and they are beside each other, there will be a transfer of heat from one object into another, whichever object has the higher temperature, until you wind up with two objects that have the same temperature because of that heat exchange. That's what we call heat transfer. Always from warm to cool until they both have the same temperature. The law of the conservation of energy says that energy is neither created nor destroyed. It simply changes its form. Well, what are the forms of energy that can possibly occur? Well, you can have heat, you can have light, you can have movement, you can have sound. It is not created nor destroyed, but it can change forms. Make sure you understand that. It can change forms. And these are just four major examples of the different types of forms that energy can have. So make sure that you know the definition for heat. Make sure you know that it goes from warm to cool always until they're the same temperature. And make sure you understand the law of the conservation of energy. When we say something is endothermic, that means that it absorbs heat. So if you have an object, remember we're going to go back to those two objects. Remember they were at different temperatures. And one of those objects had a higher temperature than the other. So endothermic means that heat is being absorbed from the higher temperature to the lower temperature. That's what endothermic means. Exothermic means that temperature or heat is going to be released. So once again, you have your two objects, they're different temperatures. One object is a higher temperature than the other, and it is releasing its heat into the other. Well, the one that happens to be releasing the heat is exothermic, because the heat is being lost and releasing heat. The one that's absorbing the heat then is endothermic. Make sure that you understand the definition of these two. This is like a highlight. Please make sure you understand that. If you can't get much of anything else, this is very important to understand. The concept of heat in is equal to heat out basically tells us that the same amount of heat goes out to what's endothermic from what's exothermic. So whatever that amount of heat is, and we're just going to say, I'm going to put this before I give you that particular term. Whatever amount of heat is released is equal to the amount of heat absorbed. Heat in is equal to heat out. So let's talk about a calorie. A calorie is the amount of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. 1 gram of pure water by 1 degree Celsius. It's the amount of heat necessary This is what we call a calorie. Now I want you to pay close attention. This is what we call a calorie. This is the symbol for calorie. And it is 1 gram of pure water by 1 degree Celsius. How much heat did it take? So you have to have pure water, not water that is has impurities in it. It would have to be pure water, like distilled water, pure water. And we measure how much heat does it take for 1 gram of that pure water to rise up 1 degree Celsius. This is what we calibrate things by. I'm just going to put that word calibrate. This is what we calibrate things by, that calorie. And again, please pay attention to the fact that that's calorie with a lowercase c. And I'll tell you why when we get a little bit further. So make sure you understand what a calorie is. It is a unit of heat. It is the amount of heat needed to raise the temperature of 1 gram of pure water by 1 degree Celsius. Specific heat is specific to whatever the substance is. So let's look at specific heat. It is the amount of heat needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. Whereas calorie is the amount of heat necessary to raise a gram of water, pure water, by 1 degree Celsius. Then if we look at other substances, we can calculate the amount of heat needed to increase the temperature of a gram of that substance by 1 degree Celsius. This is what we call specific heat. Make sure you understand the difference between specific heat and the calorie. Make sure you understand that whereas calorie symbol is CAL, specific heat has a symbol too, which is a capital C. Not only do you need to know these terms, you also need to know their symbols. So, the specific heat of water, we already said, is the amount of heat necessary to raise 1 gram of water by 1 degree Celsius. That is the specific heat of water. We know the calorie is the heat of 1 gram of water by 1 degree Celsius. But this temperature that is specific to water is going to be 1 calorie. So it takes a calorie of heat per every gram of water to raise it by 1 degree Celsius. This is the unit for specific heat, and this is the value for the specific heat of water. The unit is calorie per gram degree Celsius, but when we look at water, since we use it as a calibrator, we know it's 1 calorie per gram degree Celsius for water. Only for water. Nothing else. The unit is 1 calorie per gram degree Celsius for water. So make sure that you know the specific heat of water. Again, it's specific heat to that substance. For instance, if say like the substance was alcohol, think ethyl alcohol, it would take 0.574 calories per every gram degree Celsius. That means it takes 0.574 calories of heat to raise 1 gram of alcohol by 1 degree Celsius. If I was looking at glass, it takes 0.201 calories of heat to raise 1 gram of glass by 1 degree Celsius. Okay? So just looking at this and comparing it with water, it takes less heat to heat up alcohol, 1 gram, and it takes even less than that to heat up glass to 1 gram of glass. So those are specific heats that are specific to the substance. And it also shows us that not just, quote, solutions can be heated or liquids can be heated, also solids can be heated because glass is, of course, a solid. And when you heat it, it then turns into a flowing mass so that we can make all kinds of things. So, again, the units for heat to flow, 1,000 calories is the same as 1 kilocalorie. Notice the kilocalorie here has a capital C-A-L. I'm going to explain that to you. Whereas the calorie, which is what we were looking as a unit of heat, is just a C-A-L, and it's a lowercase. So please keep note of that. 1 joule is the equivalent of 0.2390 calories. So 1 calorie is equal to 4.184 joules. We know that the specific heat of water is equal to 1 calorie per gram degree Celsius. So if I were to convert that into joules, that means that it's also equal to 4.184 joules per gram degree Celsius. Now, before we go any further, make sure that you know this information. Make sure that you know to go from 1 calorie of water to joules, you'd have to multiply it by 4.184. To go from joules back to water, to calories, you'd have to divide by 4.184. Okay, so if I had 2 calories of water, I'd multiply that by 4.184. And if I had 2 joules, I divide that by 4.184. This one is going to give me joules for my answer. This one is going to give me calories for my answer. All right, so back to amount of heat. When we talk about the amount of heat of something, we're talking about MC delta T. This is the equation. Amount of heat is also known as Q. So Q is equal to MC delta T. Before I go on, make sure you write that down. That is the formula for the amount of heat. And then let's see what this MC delta T, etc., see what all that means. M is for mass. Capital C, remember capital C is a specific heat. Whatever we're talking about, we could be talking about water, we could be talking about glass, we could be talking about sand. The specific heat is a capital C, and it can be either calories or joules. Delta T is a change in temperature. And notice the units that we use for all this. Masses in grams. Oops, let me put it this way. Specific heat can be in calories or joules. Temperature change is in degrees Celsius. So that is going to be grams times calories per gram degree Celsius times degrees Celsius. Okay? If we use those units and cross out as necessary, grams will cancel out, degrees Celsius cancels out, and all you have are calories. If I'm talking joules, then that's grams times joules per gram degree Celsius times degrees Celsius. And in that case, grams cancels out, degrees Celsius cancels out, and you're left with joules. It works either way. So make sure that you not only know the formula for the amount of heat, which is MC delta T, but you also know that when we talk about mass, we're talking about grams. When we talk about capital C, it's specific heat of whatever the solution is. And delta T is a change in temperature, which is degrees Celsius. Okay? K, Kelvin, is 273 plus the degrees Celsius, and degrees Celsius is K minus 273. Well, why am I telling you this? Well, I'm telling you this because If I have 0 degrees Celsius, I can't do any calculations. But if I add 273 to it, it gives me 273K. Hold on. There we go. 273K, which is the same as 0 degrees Celsius. The reason we use Kelvin is because if you use Kelvin, you can do your calculations. You cannot do a calculation that's times 0. If I told you standard temperature and pressure, we know standard temperature and pressure is 0 degrees Celsius and 1 atmosphere. If I tell you this is at standard temperature and pressure, you can't multiply any of these times 0. You can't take your calories per gram degrees Celsius and multiply it by degrees Celsius if it's 0 degrees. You're going to get an answer of 0. So we convert this not into 0 degrees Celsius, but we convert it into our Kelvin, which is 273. Then you can get your answer, and you can always convert it back to degrees Celsius by taking whatever answer that is and subtracting 273 from it. And you'll see this as we go through these problems. So make sure that you understand the conversion from Kelvin to degrees Celsius and from Celsius back to Kelvin. Okay? The freezing point of water is 0 degrees Celsius, 273K. Rarely do we use Fahrenheit in chemistry, but in case you do, it'll be 32 degrees Fahrenheit. The boiling point of water is 100 degrees Celsius. Add 273 and you get 373K. And again, just so you can know, it is 212 degrees Fahrenheit. Make sure that you know your degrees Celsius and your Kelvin for boiling, your degrees Celsius and your Kelvin for freezing. Make sure you know all of those. Okay, just an aside before we end, let's talk about that K. I thought they would show that, but let's talk about that kilocalorie. Kilocalorie is designated by CAL. Why? Well, a long time ago when they were talking about food, they thought that it was a calorie of food that you were eating. When they found out it really wasn't a calorie of food, it was a kilocalorie. Now remember, it takes 1,000 calories to equal 1 kilocalorie. When they realized that they were actually talking about 1,000 calories and not just 1 calorie like they were writing in the foods, instead of changing it to K, they decided to just capitalize the C so that we know the difference between calorie, which is just CAL, and kilocalorie, which is capital CAL. So why am I telling you that? Because when you look on the back of whatever you might be eating, you're dieting, and you're thinking, hey, this only has 10 calories. You're thinking 10 calories. It is not 10 calories. It is 10 times 1,000. And that is giving you 10,000 calories. These are the ones that you burn off when you do your exercise. So while you're like, oh, it's just 10 calories, that is not true. It is actually 10,000 calories. So please keep that in mind for those of you who may be watching your calories as you eat. And that ends this section of your lecture on thermochemistry.